Welcome back for part two. I'll probably go for about an hour and a half here. So we may go a little into lunch, but we'll leave time for things. I want to make sure to do at least a little bit of learning. Okay. But mostly what I'm going to do here in part two is talk about how we build these models using the tools of probabilistic programs and some game engine simulators. Okay, and we'll spend a lot of the time on intuitive physics for a number of reasons. It's exciting to us. We're doing a lot of work on it. We've made a lot of progress. It's also the place, I think, where brains, minds, and machines best meet up when it comes to the common sense core. I will talk some about intuitive psychology, but at this point, there's interesting possibilities for using neural networks, both real and studying biological neural networks that underlie intuitive physics. And we will come to some of that in intuitive psychology. Again, you'll hear really exciting work on that from Rebecca Sachs and Vinrik Frewald tomorrow. Okay, but it's just harder representationally, basically. So we've made a little bit less progress on the computational cognitive neuroscience there, or any kind of plausible neural networks. All right. So intuitive physics. This will also be an opportunity to show you some of the experimental paradigms that we use. Now, I talked in the first part mostly about kids, right? But we do experiments on kids. I'll show you a couple. Most of the work we do in my lab is with adults, but we study the things that that young kids can do, but we study them in adults because we can get a lot more data, a lot more quantitative data, a lot easier, a lot faster by studying adults, and we think we're studying basically the same thing, okay? Although there are important differences, and we could talk about that. All right. So the kind of experiments we might do with adults here are judgments, for example, in these blocks world scenes. So blocks world is a classic setting for studying intelligence, including intuitive physics. And we might show you these stacks of Jenga-like blocks, right? These are all simulated images, but you kind of can see what we're doing, especially if you've played the game Jenga, but you don't have to have. And the question might be, well, how likely is any one of these towers to fall over under the influence of gravity, right? So I've built this stack. How stable does it look? Okay. And probably most of you would agree that the ones in the upper left here look pretty stable, and the ones in the lower right look pretty unstable, right? More likely to fall. Okay. So that's a kind of experiment we could do. Now, if we want to build a model of how you do that, okay, then the mental model that we think you have is something like this picture here, and it's about interpreting images at a certain point in time and being able to predict what's going to come next, what you might see in the future, images at a later point in time, okay, but also really about the underlying world state. So by the image, I mean the pixels, and by the world state, I mean something like a description of the three-dimensional objects, physical objects, so their shape and their physical properties, whatever is basically the state of the game physics engine needed to reason about these things, right? So we're going to use tools. We're going to model those arrows, which are the causal arrows, using game graphics engines and game physics engines. And I'm not going to tell you the details of how those work, but the key thing is that they capture in some form, they capture the actual causal processes of how graphics or optics works and how physics works, like how light bounces off surfaces of objects and forms images, or how things like Newtonian mechanics or fluid mechanics. But they capture them in only kind of approximate ways that hack various things. They for the most part, they respect physics, but the goal when you're designing game engines, right, is just for it to look good and be fun. And that means it has to look good on short time scales, but be really efficient. So because it has to support an interactive loop, right? So it's not like Pixar's graphics engines, which are designed to render beautiful, often photorealistic images, which use things like ray tracing, where you basically almost model photons scattering off objects and many interreflections. As a side note, I guess NVIDIA, that one of the leading game graphics companies, just introduced a new chip, which they say a new GPU chip, which does real-time ray tracing. So increasingly, the game industry is moving in this direction, because wouldn't it be awesome if you could have like an interactive Pixar movie, right, with that good graphics? And you will have that before too long. But the graphics engine in your head may not be that good. Although it's pretty good. I mean, I don't know what your dreams are like, but the graphics in my dreams can be pretty good. Okay. Similarly, game physics, right? In many ways incorporates insights of Newtonian mechanics, but there's a lot of hacks too. And as a result, things like you don't really have conservation of energy often, but you have various kinds of forces and key properties like mass and friction and elasticity, the things that you kind of need to model like what we did with the tape there. Okay. So let's talk about how we do probabilistic inference in this way. So vision, from this point of view, and again, I'm going to talk a fair amount here about vision, but it's the kind of intuitive physics, common sense approach to vision. It's more of a top-down in several different senses, as Jeremy and I were talking about, view of vision. That I think really does start to meet up in a pretty interesting way with some of the more bottom-up approaches to vision that you've seen from Jim DiCarlo or Gabriel or Tommy, for instance. Especially because of the community we have here in the summer school, I'll talk about vision somewhat. But from the kind of probabilistic program common sense view, vision is inverse graphics. It means taking the output of one of these approximate rendering engines, okay, viewing it from the point of view of a probabilistic model. Like there's a conditional probability of image condition on scene, and I want to make a guess at the likely scene, just like you did in those like Bayesian tug-of-war examples yesterday in the tutorial. Okay, so, or if you're watching this on the video on the probmods.org webbook. Okay, so here what that means is I'm going to see an image of like a block tower like that, and I want the output of my vision system to be something like this, which is a configuration of 3D objects which would render approximately into that image, okay, with maybe some noise model. Okay, it looks like pixel noise or some little noise model. Now you might say, well, in what sense is that 3D? It just looks like a black and white version of the one on the bottom, right? But that's just a projection of a 3D representation inside the computer. And a way to see this, it's also a sample. It's a posterior sample. So it's a sample of a high posterior probability scene conditioned on the image, okay, conditioned on some observation noise model. Now, this is one sample. Here's another sample. Here's another sample. Maybe I have 4 samples, right? So if I play those fast, you see what looks like the blocks moving around a little bit in 3 dimensions, right? So those are 3 different samples of 3D positions, right? Those are not samples of images. They're samples of block positions in 3D, but then rendered into images and coded in black and white. Okay. So, but the idea is that vision gives you maybe one of those guesses, and you see they're only a little bit different, and they all represent like plausible, a plausible distribution of uncertainty that you would get if you looked at that image for a relatively brief period of time. Okay. I should say, by the way, that the work I'm talking about in general on the intuitive physics stuff here, just for citations, is work that was done by Peter Battaglia and Jess Hemrick when they were in our group a few years ago, and published initially in PNAS in 2013, and some later work that Hemrick et al. Did in Cognition. It builds on inverse graphics work that I'm going to be talking about by Vikash Mansinga, Tejas Kulkarni, and then recently developed by people like Ilker Yildirim and Jiajun Wu in our group. But this particular image here is actually from the Battaglia et al. PNAS paper, where they built a very, very simple version of this system that would look at one of these blocks world scenes and make a guess like that at the underlying scene. Here's another example. This is a very unstable tower, right? And here's a guess at the 3D position. Here's a few other guesses. And you can see as they move around, again, those are all plausible 3D positions that could underlie this very unstable scene. All right. Now, how do we do this? How do we construct one of these posterior samples? Well, here's another use of top-down and bottom-up, or maybe it's the same use. But this system, the one I just showed you, that's a very top-down approach, and it's a very slow approach. Biologically, it's very implausible that it works this way, although it's possible you could build machines this way, and there's some things that I think are biologically right about it, potentially. Okay, but what I mean by top-down, okay, is that it's using methods, it's using the most basic methods that you saw also in the probabilistic programming tutorial. It's using a kind of Markov chain Monte Carlo. So what that means, you can think of that as like a hypothesize and test idea, but with a biased local random walk in the space of hypotheses, where you make some guess. Initially, it's probably very wrong. Doesn't look much like the image at all, and then you change it, you tweak it in some ways. You make a local proposal, like maybe you move this block here or there, you change the shape a little bit or something like that, and then you see if that's better, you're more likely to accept the proposal, otherwise you are more likely to reject it. And the key is that you make a bunch of these proposals, and you're more likely to accept the ones that are better than worse, and if you're willing to wait long enough, after hopefully not too much time, it will converge, that the Markov chain of those proposals will converge to a sample from the posterior. Okay, and the first kind of inference algorithms that probabilistic programming languages like web people were built with do that. And there's reasons they were built that way initially, because it's universal. So you can define in a Turing universal sense, if you guys know what that means, but basically you can define probabilistic programming languages so that any computable probabilistic model, that means any probabilistic model whose conditional probabilities are computable numbers, okay, can be written in these languages. And you can do, for any computable conditional query, that means for any conditional probability you'd like to know the answer to or you'd like a sample from, these MCMC or top-down or local hypothesize and test algorithms can answer that. And that's quite remarkable that you have that. Like running in your web browser when you do that tutorial, you have a universal probabilistic inference engine that can answer any computable probabilistic question. That's pretty amazing. It's just for most of them, you're going to have to wait a very long time, and that's not very satisfying, certainly not for the brain. So right now, if you look at the modern toolkit of probabilistic programming, and I'm using a phrase of Vikash Mansinga's here, inference programs or inference programming, there's a range of different kinds of, you might call them inference algorithms, but they are also probabilistic programs that run on top of basically a mental simulation program like a probabilistic physics engine. But these probabilistic programs are designed to compute the inferences, and some are very slow but general purpose, like the ones I've just talked about and used here. Others are much faster, although more special purpose. And this is where neural networks have come in, right? So I'll show you some of that in a little bit later, is ways that we can use neural networks to basically learn very fast approximate inference in probabilistic programs. But there's no free lunch in that while they are very fast, they are very specific to a particular program or program structure that is used to train them. Okay, but that might be a really good way to think about how the probabilistic program inferences work in vision, because the visual system, compared to other aspects of cognition, has a relatively fixed architecture, certainly over our own lifetime and well, at least over our own lifetime, let's just say. Okay, so the basic kinds of inferences that you do in inverse graphics, a lot of them are things that you have a lot of experience with and a lot of opportunity to practice even in your sleep, as we sometimes say. And what you learn is reusable. Whereas in other kinds of more advanced kinds of cognition, maybe a little bit less so. Okay. But the difference between these fast and slow approaches here is illustrated in this figure, where on the x-axis I have time, on the y-axis I have likelihood or log likelihood. Actually, it's log likelihood on a log scale. But what I'm showing is basically higher is better. It means in a scene interpretation, it's a better fit to the image. And I'm showing how that evolves over time, how your scene interpretation evolves. For the baseline, the red one, that's one of these top-down Markov chain Monte Carlo type approaches. And you can see it gets better, but slowly. And the blue one is a thing that uses a neural net to accelerate the inference in ways I'll show you later on, but it's much faster. Okay, it basically gets as good as the MCMC thing almost immediately. Okay, but only for a specific class of problems that it's had experience with. Okay, all right. So we'll come back to the fast methods before, but right now I'm focusing more on the knowledge representation and how to use these structured causal models, let's say these probabilistic graphics and physics programs, to do scene understanding. And I'm not going to worry about whether it's fast or slow. Okay, but I want to show you the generality of this. So here I'm showing you a few things from the Kulkarni et al. CVPR 2015 paper. This introduced a probabilistic programming language for scene understanding called Picture, which Mansinga and colleagues are kind of redoing with some of these modern tools using neural networks. So stay tuned for that. Kulkarni also, he's now at DeepMind, and with some teammates there, they've also been doing a bunch of interesting related kinds of sort of neural net enabled inverse graphics. Like you might check out their spiral paper, for example, from the most recent ICML. So another sort of similar idea building on this. Right. But for example, things we could do even just a few years ago, right, was take, for example, take the same basic framework and see blocks or see faces. So for example, we could take a generative graphics model for faces that has a probabilistic causal model in which you generate like the 3D shape of a face, the texture, you choose a lighting direction, a camera angle, and that renders an image like this. And now we can look at a face image and run that backwards. So for example, here's just a movie. Sorry, the graphics got mangled a bit. But on the left, you see an observed face. And on the right, you'll see one of these slowly evolving MCMC chains of the interpretation. So on the right, it starts out not looking very much like the face, but it makes local adjustments until fairly quickly it converges on something that looks just like the face, right? Okay. But again, the key isn't that it looks just like it, right? But that it's a real 3D model. I've just projected it into an image. But because it's a 3D model, I can now imagine what this face would look like under different conditions. So here's other examples, right? Where I'm taking a face and then I'm imagining what it would look like under different viewpoints or lighting conditions, which I can do because I've inverted the graphics engine. Okay, so this is a way to richly perceive faces beyond just classifying them, but to actually see their real underlying structure, what you might need for, say, really understanding somebody's emotions or their health, or in mate choice or other kinds of things. These might be, or a lot of social interactions are going to require a rich 3D perception of the details of the shape and texture of a face of somebody that you've never seen before. Okay, and we think these kinds of things are necessary, or at least very valuable for doing that. You can apply these things. The same framework can be applied to perceiving bodies, right? The power of having a probabilistic program and language is I don't have to separately engineer a system for body perception. I just give it a model of bodies. So in this case, like a graphics model of bodies, and then I can observe a body in this case, like here's Usain Bolt, and now you're going to see the same kind of top-down inference chain where I'm making local adjustments to a 3D body model until it looks like the image. Okay. You'll notice that it doesn't look like the image at the pixel level here because we don't require that the model match at the pixel level. In this case, it can match at an intermediate representation level, like an edge map, or it could be like convenet features, if you like. Okay, and that's useful because that way we don't have to capture like all the details of skin color for the whole body and all the clothing that can vary. We just have to capture the shape. Okay, but this system this was used to build a system that at the time was actually a state-of-the-art full 3D body perception system. We could use it for other kinds of generic objects like bottles and vases and these kind of interestingly spherically symmetric, but interestingly, or cylindrically symmetric, but interestingly shaped objects. Okay. Again, it works really well, though slow. Okay. I'll come back to in a little bit how you could use neural networks to accelerate all of these things. But the key is that the target of perception is this rich 3D percept, which then becomes the input to the physics engine, right? So if we now want to take these tools and use them to do intuitive physics, we're going to take our, say, 3D sample. Now I've drawn it as a wireframe so that it actually looks a little more 3D, I guess, not an image. But that's the state of one of these game physics engines. So I can now if I want to know what's going to happen, will the blocks fall over, I can just run the physics forward. Going forward with one of these simulators is much easier than going backwards, right? When I say, okay, well, we have a probabilistic program, it goes one direction, I want to now condition on the output and make an inference to the input, that's hard, okay? But going forward, that's always easy. And for that, I don't need any neural networks, I just need my simulator, right? So I just take my game engine and run physics forward. So it just simulates the effects of gravity, friction, collisions. And what I see if I run it on that guess of the world state for that image is, well, the blocks mostly fall over, okay? So this represents one posterior predictive sample of my probabilistic physics engine, which would say for that scene, I think that the blocks are mostly going to fall over. So it's very unstable, right? Now, with one guess, you can make with one sample, you can make a guess. You can't be confident, or you don't know your confidence unless you can take a few samples. And in the work we did here, we estimated that people we asked people to make like a 1 to 7 judgment, for example. 7 means I'm sure it's going to all fall over. 1 means I'm sure it's going to all be stable, and intermediate numbers are intermediate things. And we estimated that people took around 3 to 5 samples. But the point is that in our models and in people, we think you're taking one or a few samples like this. Here's another sample where now I'm propagating, again, the state of the objects through a few steps of the physics engine. And what you can see is that different things happen in these 2 samples, right? This is different. The outcome at the end is different here and here at the fine-grained detail level. But for the purposes of intuitive physics, for most plans we want to make, it's basically the same. Namely, most or all of the blocks fell over. So that's going to be something I would want to do something about, unless my goal is to have them fall. Okay. So to turn this into like an actual quantitative experiment and model, what we do is we have a bunch of people make, say, 1 to 7 judgments, but they could also make binary judgments, and you could average. It comes out the same. And then what we're plotting on the y-axis here are the average of a group of subjects where each dot is for one of these tower stimuli. The cross bars show error bars for both the people vertically, and the model is the horizontal prediction, where the model, again, took a few predictions like the one I showed you and looks at the percentage of blocks falling over. Okay. And what you can see is that there's a pretty good correlation, right? I picked out 3 specific stimuli, but overall, across 60 different stimuli, it's, captures most of the variance in the data. And this is a nice, one of the first good experiments we did. Actually, one of the first experiments we did, but it came out very nicely, so it encouraged us to do a lot of others. And this is, most of them look much like this. So I'll show you a few other examples. But I also want to contrast it with this plot over here, which is the same data from humans on the y-axis, but a different version of the model. You could call it an ablation or something, although in some ways, strictly, it's better. It's the same physics engine, but without the probability or the uncertainty. So this is a system which perfectly solves the vision problem. It perfectly knows where all the blocks are, no uncertainty there, and no uncertainty in the physics either. Our model has a little bit of uncertainty in like which forces are operative, exactly, like maybe the table could be bumped, or there could be a wind, or it could be various ways of inserting force uncertainty. It's hard to distinguish the different ones here. But here we have a model which has no uncertainty. It solves the vision and the physics problem perfectly. And so in some sense, it's better. It's fully accurate, but it does not fit human data nearly as well, right? The correlation with people's judgments is more like around 0.6 rather than around 0.9. And you can see the big scatter. In particular, what you can see is there's a bunch of points in the upper left here, which are things that people think are unstable. High means likely to fall, but the model thinks are either perfectly stable or mostly stable. The red dot, the red stimulus, is a classic one. So this one here, this is one of the ones I showed you before when we were showing you the inverse graphics. And if you look at this, right, I mean, I'm sure most of you would agree, it looks like it should be falling over, right? It looks unstable under gravity, right? Okay. It actually, in the ground truth physics, is stable, right? That's because the blocks are just perfectly arranged that it won't fall over. But we don't see it that way. It's very hard to see that. And the probabilistic model captures that. The ground truth model doesn't. And this is the worst mistake the ground truth model makes, but it makes others. Okay? And the reason is, right, or what the model suggests, is that this is an interesting kind of probabilistic physics illusion, that the way or at least our hypothesis here, is that the way we see the world, right, has this uncertainty intrinsic in it, right? We're not interested in especially because our perceptual system isn't perfect in solving the 3D problem, right? There's going to be some uncertainty. Then we need to propagate that uncertainty through our intuitive physics, right? Or even if we only propagate one sample, right? One posterior predictive sample typically is going to be unstable, because if you just were to change the block position just slightly, or if you got it just slightly wrong, it actually would be unstable, right? And almost all of them are unstable, which means probabilistically we should be confident that it's likely to fall over, right? But this is just one of many illusions that we're familiar with in vision, where in some sense your visual system does the wrong thing, but it's actually the right thing if you think about a rational probabilistic inference. Okay. Now, we could contrast this model. I'll show you a few other things we can do with this model, but I want to first of all contrast it with a different kind of approach, a more pure pattern recognition approach, right? Like basically end-to-end, deep convolutional neural network, okay? Which you can certainly build and get it to solve this kind of problem. And it represents a reasonable alternative hypothesis, which is which some of you might have. I don't know. Some of you may find this model compelling, the one I presented. Others might say, well, haven't we had? Do you really have to have a mental model of blocks and physics and all this stuff? We've had a lot of experience in our life with objects falling over. We played Jenga. We've played with blocks. Maybe we've just, maybe we really can take a more pattern recognition approach. And you could instantiate that idea by taking a deep network, which is fairly similar to the ones that have been used to do object recognition or detection or ventral stream modeling, but now train it end to end to map from images of stacks of blocks to several different outputs or losses. One is like, will it fall over or not? Another might be a sort of a pixel mask prediction thing. Turns out that helps a little bit to predict where the pixel flow is going to go. Importantly, this is a system which is not built with any notion of objects. It's just going from pixels to either binary classification, yes, no, fall, or other pixel mask things. It was built by a very good team of deep learning researchers at Facebook AI. And it works very well, but this is a great example of how a deep learning system can be trained to solve a particular version of a problem, but not necessarily to capture the underlying structure needed to generalize. So you train the system on 200,000 images of cubes. In particular, it works especially well if the cubes are all different colors, because then it gets nice pixel flow information. So you can train it on cubes like 2, 3, and 4 cubes, and it can generalize in some ways. It can generalize to 5 cubes. Most impressive generalizations it makes are to actually real-world images of cubes, of the same cubes. I'll show you that actually in a bit. But it doesn't generalize to much other stuff beyond that in terms of differently shaped objects, different numbers of objects, or different kinds of judgments besides the judgment of will the blocks fall over. Whereas you can generalize in all those ways without any special new training, right? So the system that we built can solve the problem I just showed you, but it can also solve all these other problems, like which way will the blocks fall, or how far will they fall? Or it can be reprogrammed in a sense because it has real representations of physical objects and their properties via language. When I talked about how natural language grounds out in these core physics representations, I can tell you, for example, that there's, as you see here in these scenes, there's 2 different color materials, and suppose I tell you that the gray stuff is 10 times heavier than the green stuff. Well, that should change your judgments. So if you look at that pair of blocks there, right, or this pair of towers, they have the same geometry, but they're colored differently, and people judge that they're going to fall in very different directions, and so does the model. Or I can show you a scene like this, where the blocks seem like they should be falling over, but they're not. And then I can say, well, do you think that maybe the red stuff or the yellow stuff is a lot heavier than the other material? So you can make an inverse inference about the density, if you like, or the mass, relative mass of the different kinds of objects. People can do that too, and our model can do that. I'll show you one other judgment, which is in some sense a kind of weird one. It makes for a fun interactive demo. We'll do that in a second. But I also want to emphasize the point here is, which is really trying to develop the point I'm trying to show on this slide, is that, if you like, for common sense human intelligence, there isn't a task, right? I mean, a basic thing about machine learning and the way machine learning, not just deep learning, but the way machine learning approaches have been deployed in AI, and this is really what I mean by basically working on AI problems as if they're pattern recognition problems, is you define a task, and then you build a data set for the task, and then you build a system to solve the task, to find the patterns in the data which solve the task. But a really basic difference between that and intelligence in the mind, right, and it's not just humans, but especially in humans, is that you built models that are not just designed or not just built or trained for a task. You can reprogram them on the fly to solve tasks that you've never done before, or maybe never even thought of. So like, consider this task. Here we have a table with red and yellow blocks, and imagine that the table is bumped hard enough to knock some of the blocks onto the floor. So do you think it's more likely to be red or yellow blocks? You guys tell me, red or yellow? Red, okay. So this is a question which you can't just answer based on previous experience of stacking blocks. Now, you could say, well, I mean, I have some other previous experience. Like, I see there's a lot more red blocks, so it's probably just that. But let's try a few others, okay? So how about here, red or yellow? How about here? Yeah, okay, good. So we could go on all day, but we'll stop there. Maybe you get the point, right? I mean, I could generate an infinite number of these stimuli, and you can see here, right? Like, there's fairly broad agreement, but some of these are harder. There's more uncertainty, or you're slower for some of those, right? And again, for those of you who've done behavioral work, I don't know if you've talked about this in terms of like psychophysics tutorials, but for many other kinds of, especially lower level psychophysics tasks that have been studied for more than a century, there are basic speed accuracy trade-offs. Some things are harder, some things are easier, and when something is harder, there tends to be more disagreement in the judgments different people make, and they tend to be a little bit slower. And you just saw that right here in your own responses. And that's totally consistent with a model that says you do something like this. You run a simulation of the underlying physics that the problem asks you to do, and maybe you run one or a couple, and if it's very clear, then you respond. Otherwise, you might run a few more simulations. The simulations in this case might look like this. So here's a simulation of one of these scenes with a small bump, and here's a simulation with a big bump. And again, the problem didn't specify big bump or small bump. You might try one or two, right? Or you might just try one and just sort of see what happens. But it doesn't really matter which of those simulations you ran, because the outcome at the intuitive level is the same, right? And also notice you don't have to run the simulation all the way to the end. So you can just run either of these simulations for a few time steps, and you already know what's going to happen, right? It also doesn't have to be very accurate. I mean, I'm showing you a fairly fine-grained accurate simulation, but you don't have to run a fully accurate simulation. It can have a lot of noise or low precision, and it'll still come out about the same, all right? Noise and low precision will bias you towards seeing things that are more unstable, but as I already showed you, and we have a lot of other evidence for this, human perception is biased in that way. So here's an example. I mean, here's what I'm showing you is the analogous kind of plot of data and model for this task. And what you can see is, the fits are a little bit worse, but basically the same as I showed you for the previous experiment. Okay, but in the previous one, that was a question of, will these blocks fall over, or how likely they fall over, which, you've probably been making judgments very much like that since you were a kid. This is a judgment that you didn't make until just this morning, unless you've seen this talk before, right? Okay, so the point is that you can do both, and the model basically fits about as well, because basically what we think the model is capturing is an engine in your head which can do all these things and so many others, right? Now, there's no learning so far. I'll talk increasingly about learning as we go on for the next few minutes. It's really hard to, I mean, it's part of the reason I'm not talking very much about it in this lecture is that it's hard and we're still working on it, which is the problem of how do you learn a physics engine. But learning in or with a physics engine is a very straightforward thing to do, and it's something I think people do a lot, both kids and adults, right? You do it whenever you learn a new physics game. There's often some interestingly different physics, some weird force, some weird tweak, something happens and you have to learn it, and you can learn it very quickly, right? You might not learn the right thing to do to solve a new level of a physics game, but you can look at some weird, interesting physics and in just a few seconds figure out kind of what's going on. Like, think about the first time you saw a touchscreen glass display like an iPhone or an iPad, right? And you see, oh, I move my finger across it and wow, it lights up or it moves or something, right? Or like the first time you saw an air hockey table like that kid. Or here, what I'm showing you, this is from some work that Tomer Ullman and colleagues have done, where I'm showing you like overhead views of some weird air hockey tables, right? Where there's like 4 pucks bouncing around. Each of them is sort of a different little world. They all are Newtonian in the sense that there's something like F equals ma, but what you might notice is that there are different forces in play, right? Like if you look at some of them, you might see what look like forces of attraction or repulsion. Do you see that? Or sometimes if you look closely, you might see that some of the different patches of ground have more friction than others. So what Tomer and colleagues did is they showed people brief movies in a number of these different worlds, just 5 seconds of a movie. They were allowed to view it a couple of times, but they were asked a number of different questions, like what forces were operative, what attracts what might repel, what are the relative masses of the different colors of objects, what are the relative friction or roughness of the different surface patches, and people can judge all of these things. They're far from perfect, and the models are also far from perfectly capturing people. This is a harder task, especially when you only have 5 seconds and you have to make a bunch of different physical judgments. But people can do this, and it's interesting that they can do it at all. They can get somewhat better if you allow them to actively intervene and move things around and do little experiments, as Neil Bramley and colleagues have shown. Okay. And then we can model this with a kind of hierarchical Bayesian inference, and I'm just sketching this here. Again, the tools in ProbMods, and you'll hear more about hierarchical Bayesian models a little bit later in today, but you'll hear more from Sam Gershman and others next week. But again, this idea, it's been a very powerful way for cognitive scientists and AI researchers to think about learning in these more structured models, is to say, well, just as I can do perception as a kind of Bayesian inference, I have a hypothesis space of scenes and a prior, I can push back to multiple levels of inference to capture more abstract, longer timescale kinds of inferences, which are like learning. So I can say, for example, in this case, I can give my system what we're calling here a meta theory. Like I can basically give it effectively Newtonian mechanics, but I can then say, well, that really generates a space of more specific theories, right? It puts a prior on space of more specific theories that correspond to different settings of the forces for what forces are operative, or what the different parameters for mass or friction are. And so the top level is given, the middle level is completely unknown, and then the bottom level is observed. Because then once I've fixed all the details of the forces and the physics and some initial condition, then it just runs, and I get to observe the output of that middle level, and I can make a Bayesian inference to the parameters at that middle level. And that's how this model works, and it somewhat captures what people do. I think there's a lot more work that has to be done to make this a better model of what people do, but it shows, at least in principle, how from a hierarchical probabilistic program point of view, you can capture this very rapid learning about a range of different ways the physical world could work. This isn't how I think babies build their intuitive physics, but it's a kind of learning you can do to tune and adapt your intuitive physics to all sorts of ways the world presents itself to you. All right. Now, I mentioned also, of course, we talked a while about intuitive psychology. I'll spend a little bit less time talking about this, but hopefully the ideas now should be intuitive, and also the kind of models and experiments. So here, again, we're trying to capture, ultimately we'd like to understand what's going on inside the kid's head in the Wernicke and Tomasello experiment, right? Or what goes on inside the 13-month-old's head who sees the chasing and fleeing. I'll show you some things stepping towards that. The basic idea here, though, is to try to formalize the intuition we all talked about of efficient action planning, right? At the heart of how humans understand action, and probably, definitely at the heart of how humans produce action, in the context that we're talking about here, which is like moving around a grounded in a local spatial temporal environment. So actions which are like reaching for things, or moving for things, or moving around and then reaching for things. I'm not talking about actions like planning your financial future, where people are probably far from efficient, or actions like planning your PhD or your research, where again, we're often far from efficient, but we still want to be efficient. But in these kinds of situations, humans and animals are very efficient, and we seem to be built from very early ages to understand people in that way by kind of doing it what we call inverse planning, assuming that the actions we see, right, that the actions we see here are the output of a planning process which is pretty close to efficient, maybe with some uncertainty, and it takes as input beliefs and desires. So beliefs are a model of the world, especially the physical structure of the world. Desires are the agent's goals. And then you have a planning algorithm which produces actions to achieve the desires efficiently given the beliefs. Now we, as observers, see the output of the planning algorithm, have to work backwards to it. Just like when we're doing vision as inverse graphics, we see the output of graphics and have to work backwards. But the same tools apply here. We can apply them in a range of settings. So we started doing this line of work more than 10 years ago with Chris Baker, and Rebecca Sachs has been heavily involved in a lot of this work too, and inspired a lot of it. But Chris Baker started just doing basic goal inference. So you're just seeing an agent move around, and there's no worry about beliefs. You just assume you and the agent have perfect understanding of the environment. But the question is just, as you see an agent moving around with constraints, different constraints, walls and holes, and different possible goals, what do you think the agent wants? And how do your inferences about the agent's goals or desires change over time as a function of how the agent moves and turns and might surprise you? Okay? And what we found, I'm just showing you a few of these scenarios. These are just little snapshots of an agent moves along this path, and we ask people at different points in time, which of the three objects, A, B, or C, is the agent's goal. And you can see all sorts of interesting dynamics where, sometimes sometimes you're just very clear from the beginning. Sometimes you can't tell, and then at some point it really resolves into these two. Sometimes, like here, you think it was A until between 10 and 11, when it's, up until point 10, you think the agent's headed for A, but then they take a step in this direction, and I think, oh, I guess it's B, right? There are all sorts of double or triple switches in these domains. I'm just showing you 4 of dozens of such situations. And you can see in these cases, there's people on the model, and they're very, very similar. They're almost impossible to tell the difference. Or here I'm showing you a scatter plot of all the judgments from this experiment overall. And what's interesting is that the correlations here are even higher than in the intuitive physics. They're very high, but they're even higher. And cognitive scientists will tell you reasons for this. It might be that people are actually on long time scales much more predictable than physical objects, at least when they're moving around simple spatial environments, and people intuitively understand that predictability. The basic structure, again, is really driven by what we've called the naive utility calculus, which is the structure of costs and rewards that the planning algorithm has to be sensitive to. So the models are actually pretty simple, but they have to make assumptions about the agent's reward structure, but they're very, I think, natural assumptions. So what we assume here is that agents get a big reward, positive utility, for getting to a goal, and they have a small cost for each step. Okay? And then they make plans which try to maximize their long-run expected utility, reward minus cost. And that's a way to get just efficient planning, but it allows you to generalize to all sorts of settings that aren't just shortest paths. They can include false beliefs because of the notion that it's expected utility, not true utility. Okay? But in this case, it's just basically like shortest paths, but there's some uncertainty because the agent could change its mind. So the agent might not know exactly what it wants or where the objects are a little bit, or you just might not know, or it just might change its mind for some reason. Okay, and that gives you some extra structure here. All right. It gets a little bit more interesting when we actually allow for more interesting kinds of uncertainty. So here I'll go into a little bit more detail about the nature of this experiment. This is later work that Chris Baker did together with Julian Jara Edinger. And Rebecca and me. And it's what we call the food truck paradigm. And I think it illustrates, in a simpler form, some of the same kinds of things you saw in the red and blue ball chasing each other. Okay. So here we have a little snapshot of a university campus. Our campus at MIT is somewhat like this. Yours might be wherever you are, where there are buildings and there are lunch spots, which are the most popular lunch spots, at least for grad students, are food trucks. So they're trucks with various kinds of different food. Like in this part of campus, there's 3 trucks that tend to come to campus. There's a Korean truck, or K. There's a Lebanese truck, L, and there's a Mexican truck, M. On this particular campus part, though, there's only 2 parking spots, shown in yellow. And on different days, different trucks get there different times. And park in different spots. Okay, so on this particular day, the Korean truck parked down in the lower left, and the Lebanese truck parked in the upper right, or the north east, I guess. Think of it as an overhead view. There's a big building in the middle, and let's say that our friendly student comes out of their office here, and they can see. This is part of the experiment. And people know this, is that they can see kind of what's in their line of sight. So in this case, the student can see that there's the Korean truck there, but they don't know what's on the other side of the building, although they know where the parking spots are. Okay. So what do? Well, let's see. So they go towards, but past the Korean truck, they go to the other side, where now they can see the Lebanese truck, but they turn around then and go back to the Korean truck. Okay. So the question is, what's their favorite truck? Mexican, yeah. Isn't that interesting, right? Yeah. Yeah, right? Okay, what's their second favorite truck? Yeah. Some of you might have been tempted to say Korean. You had to remember that Mexican was an option, right? But if you did, it's interesting that you know that, right? So what's going on here, right? Again, simple kinds of action understanding or goal inference can be done in a purely perceptual way, right? Like if there's a cup of coffee here, or when I went to reach for the tape, right? Like when I first started to go around here, that tape, remember the tape was there, you didn't know what I was doing, but at some point you saw me reach for it. It's like, okay, I guess I want the tape, right? But here, the thing that you think they want is just not present in the scene. It's only present in your representation of the agent's representation of the scene, right? If you know that they know that the Mexican truck could have been there, then that's really the only way to make sense of this as an efficient action. Or in other words, you see their path. It's obviously not an efficient path to the Korean truck, because there's a much more efficient path, but it's an efficient path subject to some false and true beliefs, a mixed set of beliefs, which you just also see together with the desires. So in our experiment, we asked people both to rate the degree of preference for each of the trucks, but we also asked them to rate degree of belief for the agent's priors before they started moving. What did they think was on the other side of the building that they couldn't see? So in this case, people say that the favorite truck is Mexican and that it's most likely that on the other side of the truck, the Mexican truck is there, as opposed to the other possible worlds. They know it can't be Korean because that's here, but it could have been the Lebanese truck or it could just be nothing. And on different days, those are all options. Those all actually happen. Okay. But importantly, it's a joint inference that they like Mexican and that they thought it was likely to be there, because otherwise it just wouldn't have made sense for them to do what they did, right? If they liked Mexican, but they knew it wasn't there, or they didn't think it was there, then they would just go to Korean if that's their second choice. Okay. So people and the model basically make those inferences. The model captures that pattern of inference of joint belief desire, as well as many others. So again, in this experiment, this was the Nature Human Behavior paper that just came out last year. There's dozens of these scenarios, and the model pretty much captures all of them. Not completely, but really captures most of them. And across different conditions, again, it's very high correlations for both beliefs and desires. And we contrast it with alternative models that ablate one part or the other. Okay. So again, I think this is really starting to show that we can reverse engineer these aspects of not just common sense physics, but also common sense psychology as it sits on top of physics. Another thing we've been scaling up to is, the way I thought of this though is more as like scaling from grid worlds, little dot worlds, to the kind of things that are more like what we do in our natural world or what AI robotics would want. So actually taking video of somebody reaching, a real person reaching for an object in three-dimensional space. In this case, there's a 4x4 array of objects. And I'll show you this movie in slow motion, actually, and you can ask yourself, see when you think you know which of those objects on the table she's reaching for. I don't know, raise your hand when you think you know which one she's reaching for. Okay, most of the hands are up by now, yeah. Some of you raised your hands early, so, but at some, by around here, this point, this is the timing thing. Most of you were raising your hands. So this black dashed line is the correct answer. This is not data from an experiment. This is actually a model prediction, which we're currently engaged in testing. This is work that Tao Gao and others are doing. It started with Chris and Yibao, but Tao is mostly driving this here. And the way the model works, the way we make these predictions, is we're using what's called the Mujoko physics engine. So this is a state-of-the-art, kind of AI tool for planning whole body or humanoid robot motion. Is, again, the idea, the robotics people really want to do this, is to plan efficient actions, like efficient reaches or efficient whole body motions, because this is really a whole body motion. It's not just moving your arm, okay? And Mujoko and other tools allow you to do this. They allow you to compute the most efficient trajectory, okay? That's the forward or causal model. That's the model conditioned on desires, make an efficient action sequence. Then we want to invert that. So we want to work backwards and say, given that what's the most likely goal input to that physically efficient motion planner? And that's what we're computing here. It's a graded computation, and that's our Bayesian posterior probability of the input given the observed outputs, or the goal given the observed action sequence. And we are optimistic that this will, at least to some extent, capture people's abilities to do this kind of Bayesian inverse planning, even with a full body motion in a complex seat. You can extend this to things which are even less like reaching. But Mujoko, or a physics engine, can handle any of these things. So, a scene like this, where you get a sense of what she's reaching for, just by how she stands up and starts to move. Or here, before she's started to move her arms at all. I mean, part of it, of course, is driven by her eye gaze. But even if you blocked off, like if you couldn't see her head, I mean, you'd have to block her, do that, block her head. Just the torso, and the arms and the legs is enough to narrow it down to at least a couple of blocks and to make a pretty reasonable guess that then when you see how she actually reaches, is likely either close or actually right. You might have been surprised at which hand she used, but okay. Or take this scene here. This is tau. So which object is he reaching for? Oops. Sorry. Well, you can tell even before he actually touches it, right? Maybe around now. But notice he's doing something weird, right? What's weird in that scene? He's reaching over something. Yeah, what's he reaching over? It's either a string or it's a plane of glass, actually. Yeah. Again, think about this from a computer vision standpoint or a biological vision standpoint, right? He's reaching over something which is practically invisible, but yet you can see it because of how he reaches over it, right? You see it mostly in the way he moves around it, right? His efficient action subject to a constraint that he knows is there. Okay, so somehow we have to be able to see that to make sense of it. And I think you're only going to be able to do that by using this kind of model as opposed to a more just kind of bottom-up, image-driven pattern recognition system. Okay, we can extend these models to what we call sometimes in AI a multi-agent setting, or more of a social setting, where now there's two agents acting and we want to interpret both of them, like the chasing and fleeing or the Wernicke-Tomasello scene. So what makes this scene here look like one person has a goal and another person is trying to help them achieve the goal? Or what makes this scene here look not like helping, but like the opposite, right? Okay. So the way we model that, we can model that too by saying that we have these models, these planning models, these utility theoretic planning models, but they now have these recursively interdefined utility functions. So we say helping is something like an agent is helping another one if the first agent acts as if it appears that its expected utility is a positive function of its expectation about the other agent's expected utility. Okay, that sounds complicated, but it's not that complicated, right? In many cultures, we have names for this, usually in moral principles, like the golden rule. Do unto others as you would have them do unto you, or do unto others as you think they would want to be done unto. Basic principles like that are at the heart of a lot of common sense morality. And in work, not work that we've done, although we've collaborated on some studies, but work especially done by Kylie Hamlin, who's another great infant researcher, and work she started doing in her PhD with Karen Wynn and Paul Bloom at Yale, and has long done in her own lab at UBC, British Columbia. They've shown that even very young infants seem to be able to understand helping and hindering type behavior like this. And we've built models partly together with Kylie and Tomer Ullman about how that works. In terms, and even shown some evidence, which I don't have time to show you here, about how even 10-month-old infants, not the very youngest, but 10-month-old infants, seem to apply at least a primitive proto-qualitative version of this recursive utility calculus in terms of how they understand when an agent is helping another one. And we show that by having actions which on their own are not uniquely identifiable as either helping or hindering, but depending on the context that the infant has previously seen, the very same action would be either helpful or not helpful based on what they know another agent knows about another agent's goal. And if that sounds like a lot for a 10-month-old infant, it is a lot. Not all the infants pass that task, but the majority of even 10-month-old infants do. Okay. I'll just show you two examples of other infant studies because, again, mostly I focus on adults, but you can actually test these models quantitatively with kids, with young kids. So with 12-month-old infants, in collaboration with Luca Bonatti and Erno Teglis, this was work that Teglis did as part of his PhD in Bonatti's lab. We tested these probabilistic intuitive physics models, and I won't go through the details of how we did it, how really they did it. Teglis and Bonatti and their colleagues did all the hard work. Voul and I contributed a little bit through some models. But basically, here the physics involved objects moving in this semi-random but physical way inside like a lottery machine or gumball machine. And then after a certain period of time of occlusion, one of the four objects appeared outside through a hole. And they varied which object was it, the rare one or the common one? You can see the rare one is the 1 type, 3 type. How long the period of occlusion was, 0, 1, or 2 seconds, and where were the objects right before occlusion? Was it near or far? And as a function of those several variables, the rational probabilistic prediction, I mean, any physicist would make the same prediction. It's like it's like almost like baby stat mech, but not even very statty. But basically, you can probably see how these would give rise to graded expectation of how likely it would be. And you could set up a surprise here. The classic infant measure is a violation of expectation looking time measure, where you show infants something that's very surprising, and they look longer, just like you might. Okay. Here, a surprise would be, for example, if you set up something where there's 3 yellow objects right near the door of the thing, and 1 blue object far away, and you have the occlusion, okay? You have the occlusion, and then right away an object appears and it's blue. Because it's like, how did it get there? It was over here, right? Okay. Another surprising thing might be if they move around for a while, and the blue one, even if the blue one was close, if the blue one is rare, you'd expect after a while they've kind of randomized, so you should see more of the common one, the more frequent one. Okay, so it turns out infants actually make all those probabilistic expectations, and we were able to quantitatively model this. So we showed that the looking time was roughly proportional to just the inverse of the probability under this probabilistic physics model. Or here's some recent work that was done by Sherry Liu, who's in Liz Spelke's lab, and she's a member of CBMM as a PhD student, and she was a student in the summer school last year. And this was work she did together with Tomer Ullman. If you really want to appreciate this, I better turn up the sound and start it over. But here you're seeing infants applying this naive utility calculus cost-reward stuff to goal inference, using principles of efficiency and indeed efficient force-based planning. So what you see here is the infant sees this. This is what the infant sees. They see one agent kind of faced with a costly action to get to a goal, and he kind of declines. Now he's faced with the same costly action to a different goal or other agent, and he accepts, in a sense. He takes that costly action. Okay, and what Sherry and Tomer showed, is that infants think the agent assigns higher value to or prefers the one that it took the more costly actions for. Now, in this stimulus, it's sort of trivial because it went for one and it didn't go for the other. But the experiment is much more carefully controlled. They always see the same, the red agent always goes the same number of times to both objects. It's just that they're faced with costlier actions for one than for the other. So they basically always take less costly actions and decline more costly ones, but they're graded in terms of what's faced. So the walls can vary in height, and they see choices of different wall heights. They also vary other physical parameters, like sometimes the costly action is sliding up a steep ramp versus a shallow ramp. Other times it's jumping over a gap that's narrow or broad. And it doesn't matter which of those it is, but in each case, the underlying commonality is that there's a more physically costly action in the sense of work done, like literally integral of force exerted over a path. That's a metric that picks out all these cases. And if you say, well, the more work you have to do, the costlier the action, and you assume that they're making a utility efficient choice, then there better be a higher reward if you're taking costlier actions. And really, quite strikingly, even 10-month-old infants make those inferences in a graded way. Okay, this is the work of Kylie Hamlins, which I mentioned, but I'll skip. Okay, so that's most of what I wanted to talk about computational models and psychophysics of common sense. The cognitive science part properly mostly wraps up there.